I am so jazzed to be joining you today from a ranch outside of a place called Cedar Edge. It's on the mesa near Grand Junction, and I'm doing a little skiing here, but I happen to be staying at a vacation rental that is actually a ranch. And so I've got in my backdrop the horses here, and also what's really cool about this place is that it happens to be on an alkaline flat. So I just talked to the rancher here, and he talked about some of the difficulties that he has with ranching on this alkaline soil. So alkaline meaning basic, and so we've got a lot of basic salts in the soil in this area. And I actually tried right before I came out to brew some tea that would have a natural pH indicator in the tea, and it's actually got acai and blueberry and pomegranate, and it's got a natural pH indicator. So I brought that with me too to see if we can see the effects of the alkaline soil on that pH indicator. So in this moment, we're transitioning into more coverage on acids and bases, and looking at eventually we're going to turn our conversation away from strong acids to weak acids, and we're going to be looking at the Henderson-Hasselbalch equation, pKa and Ka values, and looking at eventually at natural buffers, that is buffers within the body that are things ranging from the natural buffering that comes from amino acids all the way to the bicarbonate buffering system, perhaps the most famous of all of the natural buffering systems, and incredibly pertinent to the equestrian world. So those of you who are horse lovers, but also those of you who are yourselves elite athletes, much like horses that are elite athletes, using a bicarbonate milkshake is a common performance enhancer within the world of the equestrian world. And so I want to read to you actually from an article about the bicarbonate buffering system and talk a little bit about that. So it's in the Veterinary Topics article, and it says, milkshakes leave a bad taste. And at every level of racing, so much time and money are invested in each horse that trainers and owners want to find the extra edge that will help give even the most astutely trained and conditioned athlete to be more competitive. So manipulating timing of feeds, feeding, supplements can alter physical performance. One such controversial substance that has been actively administered to racehorses since approximately 1989 in an effort to enhance performance is sodium bicarbonate. Commonly known as baking soda, a milkshake is a quote colloquial term used to describe a combination of approximately 500 grams of sodium bicarbonate, glucose, and often other additives. These substances reduce acidic conditions within actively contracting muscle cells, and the milkshakes are used as buffers. So our conversation will be turning towards the latter portions of our coverage to buffering systems. So let's take a minute to see if we can't get our natural pH indicator to register this alkaline soil. So I'm going to try to move things around so you guys can kind of see the white alkaline flat in this area. In fact, you can see all around the alkalinity of the soil. So we're going to see if we can get our natural buffer to work here, our natural pH indicator. There are a lot of natural buffers too out there. I'm going to grab just a little bit of this alkaline soil. So we've got here's our natural pH indicator. Here's our very alkaline soil. You can see that there. Oh yeah. So we're getting an interesting color change as we see as we see the reaction taking place, and we recognize that this is changing from a very purpley color to an almost, it's getting in places yellowy green color. So nice natural pH indicator there in the pomegranate blueberry acai tea. Awesome. In addition to engaging in the hydrogen bonding behavior that we've talked about, water is also constantly ionizing. So this notion that water ionizes is an important one to acid-base chemistry, and we can write an equation for the ionization of water. This equation being the more complete of what is commonly oversimplified, in which water can form a hydronium and hydroxide anion. This equation is commonly simplified in order to work more simply with the ion product of water. And you might recognize that we could write a dissociation constant for this, products over reactants, concentration of H plus times OH minus over concentration of water. And this value, thus, dissociation constant, is a known constant. And along with knowing the molecular weight of water, we can actually derive the ion product of water. That is to say, this numerator has a very special name. That is the Kw, or the ion product of water. So Kw we can see as being equal to H plus times OH minus, and that at 25 degrees Celsius room temperature, that product is equal to 1 times 10 to the minus 14th molar squared. Now we can derive that, and I have a longer vodcast if you'd like. Let me know where we derive that. But for now, to recognize that that's a constant. So the more protons in a solution, the higher the concentration of H plus, right? And then that means by default that the lower the concentration of OH minus, but no matter what, the product of the two stays constant, equaling 1.0 times 10 to the minus 14th. But let's think about if we were looking at pure water. In pure water, we recognize that H plus equals OH minus, and in which case we can do a simple substitution where we can say H plus squared, right, substituting in for OH minus H plus, is equal to 1.0 times 10 to the minus 14th molar squared, and then just simply taking the square root of both sides of that equation, we recognize that H plus in pure water is 10 to the minus 7th molar. Now this may be ringing a bit of a bell, 1.0 times 10 to the minus 7th. And as we think about what H plus, or the concentration of hydrogen ions, measures in solution, we're probably starting to ring the pH bell. And you're starting to think about the fact that this, because this value of H plus ions is typically an inconveniently small number, we tend to express instead the pH of a solution. So Sorensen developed in 1909 that equation for a pH. So we're going to take a look at that equation. But as we work our way to doing so, I think it's important to return to this ion product of water, and remembering that here, obviously, we see that the two are equal, 1.0 times 10 to the minus 7th. But if we were looking, say, at something like human blood, in blood, the concentration of H plus is equal to 4.0 times 10 to the minus 8th, which means that the concentration of hydrogen ions in blood is just slightly less than what we would see in pure water. And so that means that the hydroxide anions are slightly higher in concentration, meaning that blood is just slightly basic. So we're going to look more at how that situates in a biological system. But let's now look at pH. The pH scale is a convenience scale. That is, pH is a logarithmic quantity used to measure the hydrogen ion concentration. And because hydrogen ion concentrations are so low, that's inconvenient. And so pH allows us to express them in much more convenient whole numbers that resonate a lot more with us. So we can write an equation for pH, recalling that pH is equal to negative the log of the hydrogen ion concentration. Another way that we can restate that equation by rules of log is that pH is equal to the log of 1 over the hydrogen ion concentration. This is a really lovely expression because it shows us the inverse relationship between the hydrogen ion concentration and the pH. That is to say, the higher the hydrogen ion concentration gets, the lower the pH gets. We can also express this if we like, if we want to be able to calculate the hydrogen ion concentration when we know pH. We know this is base 10 log, so this would be equal to 10 to the minus pH, which is another really convenient expression depending upon what we need. Now, let's return to pure water. And of course, we recall for pure water, we had just calculated that the hydrogen ion concentration is equal to 1 times 10 to the minus 7th. So we can easily use our pH equation to calculate the pH for pure water, negative log of 1 times 10 to the minus 7th. And by rules of log, we know that log of the base A of a to the x is equal to x, so 7. That makes sense. pH of a pure water solution at neutral of 7.0. Now, recognize if we were instead wanting to look at an acidic solution in which, say, for example, a strong acid had been dissolved, such as hydrochloric acid, we recognize hydrochloric acid as being a strong acid because it dissociates completely in water. So this strong acid plus water working as the base. Now we're using Bronsted-Lowry definition of acids and bases, in which an acid like hydrochloric acid donates a proton and a base accepts a proton. So the hydrochloric acid donates a proton and forms its conjugate base, the chloride anion. So this is an acid conjugate base pair. And of course, the base, water, and its conjugate acid. So we recognize the complete dissociation of hydrochloric acid and water, and simplified, most will write this way. And this allows us to make an important assumption. That is, if we know that we have a solution of hydrochloric acid that is a 0.01 molar solution, then we can assume, because of complete dissociation, that the concentration of hydrogen ion in that solution is equal to 0.01. We can now calculate the pH using our trusty equation, negative log of the hydrogen ion concentration, which is 1 times 10 to the minus 2. And we go ahead and calculate pH as being equal to 2. Hey, that makes sense. Acidic, right? This is an acidic solution made from a strong acid dissociating in water. But what instead if we were looking at a base? Say, for example, we wanted to look at the strong base sodium hydroxide. So let's write this over here. Now we're thinking about sodium hydroxide, a strong base. And if we have a solution of sodium hydroxide that is equal to 0.01 molar, why then we now know that the concentration of OH minus, by same arguments, is equal to 1.0 times 10 to the minus 2. However, in order to plug into our pH equation, we first have to calculate the concentration of hydrogen ion. No problem, right? Because we know the Kw. So if we recall that the concentration of OH minus times H plus is equal to 1 times 10 to the minus 14th, then we can easily plug in to calculate H plus as being equal to 1 times 10 to the minus 14th divided by 1.0 times 10 to the minus 2. And we now see that the concentration of hydrogen ion is equal to 1.0 times 10 to the minus 12th. Excellent, because now we can plug into the pH equation, recognizing that pH is negative the log of 1 times 10 to the minus 12th, or pH is equal to 12. Excellent. Qualitatively, that makes sense because this is going to be a basic solution. That's extra cool.